Good evening, ladies and gentlemen. I'm Robert Dijkgraaf, the Director and Leon Levy Professor at the Institute for Advanced Study, and it's a great pleasure to welcome you at this kind of sold-out event, a public talk that coincides with our semi-annual Board of Trustees meeting. It's a particular pleasure to welcome our trustees to this event. Just as a practical matter, we will have a lecture, and then at the end of it there will be a question and answer period. Now, our speaker today requires little introduction. It's Nima Akani Hamed, who is a professor, of course, in the School of Natural Sciences at our institute. And the title, you already see it behind me, The Inevitability of Physical Laws, with the subtitle, Why the Higgs Has to Exist. Now, Nima was particularly firm on this because he kind of very publicly announced that he was willing to bet a year's salary if the Higgs boson would not be found. And one of the most pleasurable experiences of just the first few days of my tenure here was that on the very early morning of July the 4th, we had a very special fireworks because we had a champagne toast to the discovery of the Higgs particle, and actually that champagne was at the cost of somebody who had taken up that bet. And so I'm happy to report it was a high quality champagne that we drank. Nima is somebody who kind of expresses his kind of wonder and enthusiasm about physics in a quite unique and powerful way. Although both his parents were physicists, he described himself to be as an act of teenage rebellion to study physics anyhow. And so I think actually this is a very clever act of reverse psychology on behalf of your parents. Thank you very much. You studied at the University of Toronto and earned your PhD in physics from the University of California in Berkeley in 1997. Nima worked as a postdoctoral fellow at the SLAC National Laboratories before becoming an assistant and then associate professor at Berkeley. In 2002, he moved to Harvard to become a full professor there, and he remained there until he joined our faculty of the Institute in 2008. There is an endless list of honors that Nima was awarded. I just mentioned the Sloan Fellowship, Packard, the Gribov Medal of the European Physical Society, and the Raymond and Beverly Sackler Prize. But I think in many ways this was kind of topped by a prize that was awarded at the end of July, when in that month we had another piece of excellent news, which is that Nima, along with 3 colleagues here at the School of Natural Sciences, was among the first winners of the Fundamental Physics Prize. And that's a remarkable recognition of groundbreaking contribution to theoretical physics, and it included a very generous award of $3 million to each of the laureates. And you might kind of wonder whether, Nima, you would still have bet your year's income if you would have known that. In fact, we are especially delighted that the creator of that prize, Dr. Yuri Milner, is here to kind of celebrate that. So, warm welcome to you. Nima's work on particle physics and its connections to experiment is truly visionary. There's a long list of his achievements, but all of them, I think, stand out in terms of a very fresh and broad way of thinking, very unexpected way of thinking, and that has enormous traction both in the theoretical and in the experimental world. And he, for instance, has radical ideas that there could be very large, in terms of physics speak, extra dimensions, completely revolutionized parts of theoretical physics. And he has also played a leading role in how these modern theories, what their implications are for the great and exciting experiments that are going on now at the Large Hadron Collider in Geneva. After the announcement was made of the discovery of the Higgs this summer, the New York Times quoted Nima as saying, "It's a triumphant day for fundamental physics. Now some fun begins." And I think that fun is can't think of better hands to put that fun than in Nima's. And I hope that you will join me in welcoming here to the stage. Nima Akani Hamed.
Well, it's a really tremendous pleasure to be giving this talk today. As you all know, the Higgs was discovered, politically correctly speaking, a Higgs-like particle was discovered at CERN back on July 4th, and there's been an endless slew of descriptions of what the Higgs is and what the associated ideas are in the popular press. And they all use one variety of metaphor or another to describe the physics. Now, there's a problem with talking about the Higgs that almost all these metaphors are just terrible, and they don't actually reflect what's really going on. But all of us, I've used these metaphors myself, so I'm not besmirching anyone else. But for the purposes of this talk, I decided that I would try to do something very dangerous, which is to try to explain what's actually going on. Okay? I take some inspiration from the spectacular talk Juan Maldacena gave here a number of weeks ago that I hope many of you were also at. Juan's talk was really precisely correct. He used analogies, but the analogies were not just random analogies. They were really precisely, in a very sharp sense, correct. And I'm using that as an inspiration here as well. The talks are going to be completely complementary. And in a few places, I will talk about what the sort of connections are between these two ways of thinking about things. One aspect of the story that I really want to highlight and emphasize, and it's a broader point than just the Higgs. We're going to use the Higgs as an illustration of this general point, is often when we talk about what's going on in physics, I think if you're not a professional physicist, you might get the sense that these are a group of people who are just pulling things out of thin air, left, right, and center, and somehow they describe nature sometimes. Maybe other times they don't. And, you know, whether they work or not work is dependent somehow on their sense of aesthetics, what's pretty, what's good, what's bad. But it seems perhaps very dependent on the people who are thinking of these ideas. And what's not, I think, commonly appreciated, which is what I really want to stress in this talk, is we understand so much about the way the world works that a lot of the broad outlines of what even possible candidate theories that could describe nature can look like are just forced on us. There's nothing we can do about them. There's no choices. There's no 10,000 other way things could go, and we're choosing some of them because we like them, because they're pretty. The way the world works is very, very largely constrained by the laws that we know already. There is an inevitability about the structure of the laws of nature, which is what I want to talk about. And a particular example of this kind of inevitability, this incredible power we have in our understanding of how things work, is going to lead us to why it was that so many of us, certainly not just me, many people would have been willing to bet years of salary that the Higgs had to exist. But why it is we knew. I mean, if you think about it, this is kind of amazing. There's this group of people, a few theoretical physicists wandering around the world, who knew when this experiment is done, this big experiment is done, this particular measurements are made, this thing must happen. We just knew that ahead of time, and it happened. So why were we so confident? Why are we so sure it had to happen that way? That's what I want to convey in this talk. So let's start just with a review of what we know about the world. So the most basic sense, we know there are things out there made out of matter. Matter is made out of atoms. And in atoms we have, so here's a hydrogen atom, we have an electron going around a proton. And if we take a peek inside the proton, we now understand that the proton is not actually a fundamental point-like particle. It's itself made out of other particles called quarks. So the proton is made of 2 up quarks and a down quark. A neutron, another constituent of the nucleus, is made of 2 down quarks and an up quark. And this matter is acted on by various kinds of interactions. We know there's 4 basic interactions, 2 of them that people knew about for a very, very long time, gravity and electromagnetism, and 2 that we discovered really at the very, very end of the 1800s and the early 1900s, which operated very short distances, the strong nuclear force So inside a nucleus, for example, we can have 2 protons and two neutrons here. This is in a helium nucleus. And you might wonder why these protons manage to stay inside the nucleus. They want to repel each other by their electric repulsion. Well, early on, there was something that people imaginatively called the strong force that kept them inside the nucleus. We now understand that this strong force is a residual of something else that we'll talk about a little more. And finally, there was something called the weak force, or the weak interaction, which is ultimately responsible for radioactivity. If you take a neutron out in empty space, it sits there for 15 minutes, and then it disintegrates. It disintegrates into a proton, an electron, and something called an anti-electron neutrino. Now, 15 minutes is a gargantuan time scale compared to all the various times in atomic physics and nuclear physics and so on. So that's why it was called the weak interaction. That had to be something incredibly feeble that had to take so long in order to do this. But this is ultimately what's responsible for radioactivity. And these interactions, acting on the matter that we know and other particles that we've discovered since, hold sway over an enormous range of distances, all the way from the size of the observable universe, around 10 to the 28 centimeters big, down to, as we go down to shorter and shorter distances, there's something exciting happening at almost every factor of 10, shorter and shorter distances. Galaxies are 1 million times smaller than the universe. The distance between the Earth and the Sun is like 10 to the 13 centimeters. People are like 1 meter big. Atoms, protons, and neutrons are around 10 to the minus 14 centimeters. Incredibly tiny, around 1 million times smaller than the atom itself. And finally, we go down to this very, very short distance scale we'll talk about a lot in the rest of the talk, around 10 to the minus 17 centimeters. It's called the weak scale. That happens to also be around the frontier of what we're probing with very, very high energy accelerators like the Large Hadron Collider. We're actually probing these very, very tiny distances. Now, a remarkable thing that we've discovered is that actually all of these things, this whole collection of stuff, the matter and the interactions, are described in a completely common way, in a completely common language. So if we start with the most familiar, interactions, just the electromagnetism, like the electric repulsion between a pair of electrons, and gravitation, it turns out that both of these interactions are associated with a little stick figure like this. Electrons interact with a photon. Here they can interact with a graviton. The thing which interacts with the photon is actually the charge of the electron. The thing that interacts with the graviton is, in the Newtonian picture of the world, the force of gravity has to do with masses. The more and more massive an object is, the bigger and bigger gravitational force you have. But we now know, because of relativity, E equals mc squared. So really the thing which is the analog of charge for gravity is the energy or the momentum of the particle. So there's a charge associated with here, which is like the charge, which is the normal electric charge. And the analog of the charge when it interacts with gravity is energy and momentum. So there's some basic little stick figure interaction like this. And everything else which actually happens when we take electrons and photons and make them interact just comes from putting these pictures together. So if I want to have 2 electrons banging into each other, what's really going on is two of these basic building blocks and exchanging a photon there between them. So in a specific sense that I can't illustrate with these pictures, but which is really there precisely, there's some sense in which there's not a real photon, but what's called a virtual photon, something that's sort of quantum mechanically fluctuating out of the vacuum, which is what's giving rise to this force between 2 electrons. And you can see the force between 2 electrons gets weaker and weaker as you go to larger and larger distances. That tells you something. It tells you that the size of these quantum mechanical fluctuations is weaker and weaker at larger and larger distances. It's stronger and stronger at shorter and shorter distances. And that's a sort of a basic consequence of the Heisenberg uncertainty principle. But anyway, that's the picture we now have for the simple fact that 2 electrons can, for example, scatter against each other just by repelling each other via their charges. And you can put these together to make all sorts of complicated processes. So all sorts of complicated things happening in the world, in the end, just come from gluing together these basic little elementary interactions. Now, the strong and the weak forces don't look like that at all on the face of it. They look completely different than the electromagnetic force and the gravitational force. But the amazing thing that we learned in the second half of the 20th century is that, in fact, all of these forces are described fundamentally in exactly the same way. That if you go to short distances, you discover that what's really giving rise to the strong force is exactly the same kind of stick figure. Instead of having electrons interacting with photons, we have quarks interacting with something called gluons. Okay? So this is what's responsible for the strong force. The weak interactions are associated with, instead of having two electrons interact with a photon, we can have an electron and a neutrino interact with something called the W boson. It looks just like the photon. All the pictures look exactly the same. There are little detail, there's some few detailed differences. Here, for example, so far in all the pictures, it was the same kind of thing. Quark, 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 electron, electron. Here we get something a little new. We have an electron and a neutrino. But it's not really fundamentally different. For the quarks, these are the weak interactions now. We can have an up and a down interacting with this thing called the W boson. And it turns out they have a cousin called the Z boson that does just connect, for example, an electron, and a Z. So fundamentally, at short distances, they look identical. Essentially identical. So why did we think they looked so different? Why do we know about gravity and electromagnetism for centuries and centuries and only found out about these other guys like 100 years ago, 110 years ago? And the reason is that the apparent enormous disparity between these forces is a kind of a long-distance illusion. For example, let's talk about the strong interactions. So we have the quarks interacting with these gluons. Now, we have electrons and photons. We've seen electrons and photons out there in everyday life. How come we haven't seen the quarks and the gluons out there in everyday life? It turns out to be a detailed effect. It's a very important detailed effect. It's a detailed effect that earned some people the Nobel Prize back in the 2000s. But it's really a detailed effect that because of some subtle quantum mechanical reasons, the force between, the interaction strength between quarks and gluons gradually gets stronger as you go to longer and longer distances. Very, very gradually gets stronger. And eventually, at a long enough distance scale, it becomes so big that it traps the quarks and the gluons and everything else inside the protons and the neutrons. So we say that they're confined. This is at a very long distance scale. A long distance scale to a particle physicist is around 10 to the minus 14 centimeters, a million times smaller than the atom. Okay? But this is, to us, is a gargantuan, very, very big distance scale. Okay? But this is a detail. It's a very important detail, but it's a detail. Fundamentally, it's the same thing. Fundamentally, we have these same basic stick figure interactions. What about the weak interactions? Well, the reason why it took so long to discover the weak interactions, the reason they're so weak is even simpler. The photon is a massless particle. Because it's a massless particle, it doesn't cost, as we go to longer and longer distances, it's sort of possible to get longer and longer wavelength excitations of the photon that have lower and lower energy. And so no matter how long distances you go to, you get some force from it, some reasonable size force from it. Granted, it gets weaker as we go to long distances, but it's still visible, and we talk about it. It's the famous inverse square law. The difference is just that the W particle is massive. It's not massless. It's massive. And because it's massive, it really costs an enormous amount to excite it out of the vacuum. So the range of this weak interaction is very short range. The W boson is so massive that the effective range of this interaction is something like 10 to the minus 16 centimeters or so, which is 100 times smaller even than the atomic nucleus. But again, it's a detail. If we go to short enough distances, everything starts looking similar. This is the real reason we want to build high-energy accelerators and go to short distances in our part of physics. It's not so much because often when people talk about this, they talk about wanting to understand what the building blocks of all matter are and things like that. Maybe that's what some people care about. It's not so much what I care about. I think it's not a lot what many of my colleagues care about. After all, understanding, all the different building blocks of matter sounds something like chemistry. And I kind of flunked chemistry a number of times, so it wouldn't thrill me to be doing something like chemistry. No, that's not why we actually do it. We go to short distances because we've learned in this way. We've learned that the essential unity, simplicity of the laws of nature become manifest. They're hidden at large distances by a variety of accidents. But when we go to short distances, we finally see them. I mean, this is a really extraordinary fact that we see for the first time all these different interactions described in a common way, a common language, just one set of stick figures describing everything. It's pretty amazing. Okay? And we discovered that by going to short distances. So it pays to go to short distances because then you see what's really going on with the fundamental laws of nature unvarnished, not hidden by these relative accidents. It took us 2,000 years to go to distances short enough to see that all this was true. But then we see it's true. We've learned something really profound about the way the world works. Okay, so now, for a lot of the rest of the talk, maybe I should have said this at the start. This is not the most conventional description of the Higgs and all of this physics. And it might require a little bit more audience engagement. So we're going to be thinking and counting on our fingers a lot. Okay, so but we're going to have to count a lot. Actually, one hand will probably suffice. Let me think about it. Yeah, one hand will suffice. Okay, but you're going to see these numbers floating around: 1/2, 1, 3/2, 2, 0, and so on. So just be forewarned that we're going to see a bunch of numbers floating around. Okay, all right. Now, there's a really important property that particles have. It's actually one of their defining properties. It's one of the things that labels what a particle is. The particles have something called a spin. So you can think of an electron very loosely as it has some charge, and it's spinning around. It intrinsically has some spin. It can spin in some direction. Now, so there's some angular momentum that's associated with that spin. But this is really an intrinsically quantum mechanical thing, and the amount of that angular momentum that it has, it turns out that Planck's constant, h bar, this is Planck's constant of quantum mechanics, h bar is units of angular momentum. So we can actually measure this angular momentum in units of h bar. And it turns out that all these angular momenta come in multiples of 1/2. So we can have no angular momentum, 0. We can have angular momentum 1/2 times h bar. We can have angular momentum 2 times 1/2 times h bar. So 1 times h bar. Or 3 times 1/2 times h bar. 3/2 h bar, and so on. That's the list of allowed spins we can have. Okay, 0, 1/2, 3, all this stuff. And the particles that we know and love, okay, they have relatively simple spins. So the electron has spin 1/2. The photon, as it's moving along, has spin 1. The graviton turns out to have spin 2. These W boson and the gluon and the Z boson also have spin 1. Okay, so we have relatively simple numbers floating around here. Okay, so the particles you see are really extremely simple. In fact, it's just the fundamental particles that we see just have spin 1/2, 1, and 2, nothing else. So here we are. The electron can interact with the photon. I don't know why I put a W there. So that's 1/2, and 1. The electron can interact with the graviton, 1/2, 2. 3 gluons can interact. They all have spin 1, and so on. Okay? But so now we see two kinds of simplicity. First, the basic interactions are just these little stick figures. And secondly, the spins that are involved are incredibly simple, just 1/2, 1, and 2. Okay? And you don't have to look at this in detail, but in fact, we know about more particles than the familiar ones, but the whole menu of everything that we know of in this thing called the Standard Model of Particle Physics is just exactly the same. It's a bunch of particles of spin 1/2, of spin 1, and one particle of spin 2, which is the graviton. There's something special about gravity. Gravity is completely universal. It interacts the same with everything. So there's one particle of spin 2, the graviton. Everyone else is just a collection of things that are spin 1/2 and spin 1. And there's a big collection of them. There are particles that some of which you've heard of, like maybe electrons or the quarks that we talked about. There are more exotic ones, like, for example, the top quark is the heaviest of all the quarks. It was discovered in the mid-1990s. It'll play a role in the later in our story. Okay, so now that's something that we know describes nature. But now I want to ask another question. Why is it so simple? Okay. Now, part of it doesn't look all that simple. The actual menu looks a little bit complicated. We have all these different kinds of particles, and they have different names and stuff like that. But the basic structure is incredibly simple. Why these little stick figures? And why do we only have these simple things? Spin a half, spin one, spin two. Why don't we have more complicated things? It could have been much more complicated. Okay, so here are two questions you can ask. Why are the simple fundamental interactions look like A, B, C? Only 3 guys. Why don't we have a fundamental interaction that like interacts 12 guys together? Okay? That would be terrible, right? Because then we'd have to glue these together in like 100 ways, and it would be a horrible mess. But we don't get that. All we get is this. Why is that, first of all? And secondly, why is it that we have such a tiny menu of spins that we can talk about? Why do we only see a half, 1, and 2? Okay? Now, this is an example of what I was referring to earlier as inevitability. This is something truly remarkable that we've learned in the, we've known for a long time. It's a sort of a bedrock. It's a very important piece of our current understanding of reality. And it's the following slogan. We don't understand everything about physics, by far. Definitely we don't. Okay? But what we understand so far is powerful enough to tell us the following. Whatever the heck the ultimate theory is, just the laws of relativity and quantum mechanics together, we need both of them, both relativity and quantum mechanics, guarantee the following amazing fact, that at long enough distances, it'll be clear what I mean a little later, but long enough means anything that we care about, that we could interact with and know of and so on. At long enough distances, first of all, the only things that are going to matter, the only things we could possibly detect that will matter for the interactions are these basic little stick figure interactions, A, B, C. Okay? So we don't get these horrendously complicated things, A. And B, now, I'm telling you this is a consequence of relativity and quantum mechanics. What I mean is, the laws of relativity and quantum mechanics are very general principles. Okay? We have our specific universe. Of course, we care a lot about our specific universe. Okay? But these laws of relativity and quantum mechanics are very general principles. And so, as theorists, we could imagine what all possible consistent worlds could look like that were consistent with those laws of relativity and quantum mechanics. So let's do that exercise. Okay? Let's take what we know, relativity and quantum mechanics, imagine what all possible consistent worlds could look like. And the answer is all possible consistent worlds at long enough distances, again, they have to have these basic interactions, and the only spins that can possibly make sense are the following: 0, 1 half, 1, 3 halves, and 2. Okay? Now notice that so far we've seen 1 half, 1, and 2. We haven't seen 0, and we haven't seen 3 halves, but it's not in contradiction with this, certainly. Oh, and by the way, the spin 2 guy is totally unique, and it's gravity. It's the thing that's associated with gravity. In other words, this understanding tells us that this guy is totally unique. There could be a whole bunch of these guys. There could be a whole bunch of these guys. There could be a ton of these guys. In principle, this guy is very special. We'll come back to that as well. You can have at most 8 of those guys, it turns out. Okay? But anyway, we'll come back to that a little bit later. Okay? So this is a claim, and now I want to explain to you where this claim comes from. But actually, before getting there, this is a good spot to just echo the sort of title of my talk. This fact is an example of what I mean by inevitability. You don't know it ahead of time. We have these general principles of relativity and quantum mechanics, and they have as a very surprising outcome this fact that inevitably, no matter what, things have to be described in this particular way, with this particular tiny menu of particles interacting in this very specific way. Another set of words associated with this are rigidity. The laws of physics are incredibly rigid. You can't mess with them. Okay? You get what you get. After some basic principles, you don't have choices. So it's not like we're sitting around and I like leprechauns and you like fairies and we invent different stories. What we know already is incredibly rigid. Okay? Now there's a fascinating flip side of the rigidity, which is that they're also very fragile. Okay? What do I mean by fragile? It means that if you now try to monkey with the basic principles, you will make it break immediately. If you say, you know what, I don't like relativity. Let me just throw out relativity a little bit. You'll completely smash this inevitable, everything comes out in this unique, fantastic way. Okay? So these are two remarkable flip sides. Laws are very rigid and they're very fragile at the same time. They're very rigid within the structure we have, and they're very fragile to monkeying with the structure. Okay? And finally, these things, often in physics and in mathematics as well, people will talk about beauty. Ideas are beautiful and nice and so on. What we mean by beauty is this, actually. It's not, it's a very specific notion of beauty. Things that are beautiful, ideas that are beautiful, theoretical structures that are beautiful have this feeling of inevitability and this flip side of rigidity and fragility about them. Now, this is something that I could go on and on about for a long time, but I shouldn't do it because probably, to my mind, the greatest popular physics book of all time is this book by Steven Weinberg, Dreams of a Final Theory. If you haven't read it, I very, very strongly urge you to read it. And this whole theme of inevitability and rigidity and fragility and so on is beautifully discussed there amongst a number of other things. Okay. Anyway, that's the claim. So now I want to give you an idea for why the claim is true. Right? So we're going to now do a couple of things. I first want to tell you why it is that no matter what's going on fundamentally, at long distances we can't have the basic interactions that we can have, only have to have this ABC variety first. And then after we do that, I'll tell you why they only have to involve these very special pattern of spins. Okay? And I'm going to try to do everything as honestly as possible, but there's a couple of spots where you'll just have to believe me. Okay? Now, actually, our foray into this subject is going to start with something that's incredibly prosaic. Incredibly prosaic. We're going to talk about units. Okay, that sounds like the most boring subject in the world, but it's actually not boring. There's something extremely important about units. Normally, we have all kinds of units, meters, joules, all sorts of different units. And it's really hard to keep track and remember what they are. Certainly, at least when I was in high school, this was the bane of my physics education existence, was remembering what all the units were and how you converted between them and so on. And there's actually a good reason why it's so confusing. Because the normal way we talk about units is a completely human artificial construct. When we talk about distances, when we say like, so-and-so basketball player is 2 meters tall, okay, what do we really mean? What we really mean is that some people in Paris a long time ago put a bar somewhere, okay, a bar of metal, and this bar of metal they called 1 meter. Okay, so what we really mean is if we were to go take that bar out of Paris and lay it next to this guy twice, we'd get the same thing, right? So everything is actually, there are no units really. It's always two things relative to each other, right? So when we say something is 2 meters, we're comparing things to this bar in Paris. When we say it's kilograms or whatever, it's some other weight in Paris. Sorry, I don't know why these things are in Paris, but anyway. Okay, but that's not very reasonable. That's completely artificial human construct. So there's something else that we can do, which are called natural units. They're, as it sounds, they have to do with nature rather than to do with human beings. And also there's something else that's very important. Our world has both relativity and quantum mechanics. So there's a speed of light, which is an important constant, and Planck's constant of quantum mechanics, which is an important constant. And these constants let us actually switch between, for example, here's a familiar one. Time and distance, we can actually measure with the same units. I can say that the distance from here to there is 3 times 10 to the 8 meters, or I can say it's 1 light second. And it's exactly the same. It's the distance that light travels in 1 second. So that's what lets me trade back and forth between time and distance. Similarly, energies and times can be related through Planck's constant. And energy times a time has the same units as Planck's constant. So what we say is that we work in units where these constants are 1. H bar and c are Planck's constant, and the speed of light are set to 1. And what that really means is that we can determine all the units that we know and love in terms of one basic unit. We can make that unit anything we want. We can make it energy, we can make it time, we can make it mass, we can make it distance. Okay? And starting from 1, we can get to all the other ones. So let me give you an example. So in particle physics, we tend to use this unit that's 1 giga-electron volt. So it's a unit of energy. But actually, a very interesting fact about it is that energy is almost the same as the mc² energy of a proton. So this is around 0.938 GeV, but let's just call it 1. Okay? So the mass of the proton is around 1 GeV. Okay? So whenever you see 1 GeV, just think of it as the mass of the proton. Now, in these units, I can then translate everything into one unit, for example, GeV. For instance, so here's me. So my height is around 10 to the 16th inverse GeV. Okay? 1 over a GeV is units of length. Okay? So you see 1 over an energy has units of time. Time has units of distance. So I'm around 10 to the 16th inverse GeV. Now, this is an incredibly useful way of talking about my height. Let's say you're going to talk to someone in Alpha Centauri and tell them how tall am I. It would do them no good to say, if you go to Paris and put me up next to this bar, right? That would be no good. But you see, the size of the proton, 10 to the minus 14 centimeters, is around its inverse mass is 1 over a GeV. So when you say I'm 10 to the 16th inverse GeV high, you say if you put 10 to the 16th protons end to end, you get me. That's very useful information. They know immediately because the protons there are the same as the protons here. My mass is around 10 to the 29 GeV. Okay? That's really useful too because it tells you how many protons I'm made of immediately. Right? That's most of my mass is so there's around 10 to the 29 protons in me. If you're very lucky, and the lecture time will be around 10 to the 27th inverse GeV. Okay? The LHC energies, the energies of the protons in the LHC are 7,000 GeV. Okay? So these are the sort of natural units that we use. Now, when we work with these units, we discover something remarkable right away. So let's look at something that's very familiar. Let's say we look at the force between two electrons. So you remember from high school probably, the force between two electrons is a charge, and it goes like 1 over the square of the distance between them. Okay? But if you just use the rules I told you, it's very easy to see that force actually has units of 1 over length squared. So that means that this charge times charge, this charge squared, is just a number. See, the units of force are the same as units of 1 over r squared. So this charge squared is a number. Turns out the number is around 1 over 137. It's just a pure number. That's extremely interesting. The electric force is associated with a pure small number. It's around 1 over 137. By contrast, if we look at the gravitational attraction between two electrons, you'll also remember from school that it's the Newton constant times the mass of this electron times the mass of that electron over r squared. And so that tells you that Newton's constant in these natural units has the units of length squared. Okay? So g Newton in these units is around 10 to the minus 33 centimeters squared, and that length is called this famous Planck length. This is Planck length squared. Okay? So this is a minuscule number compared to everything that we know in nature, and the fact that it's minuscule is reflecting how weak gravity is compared to all the other forces. It's a direct reflection of that fact. But you notice that it's not a pure number. Okay? It has units. And that means that it's not actually true that in some sense the gravitational force is weak. You see, in some very meaningful sense, the electric force between two electrons is weak. The actual strength of the interaction is a small number. Okay? But here, it's not a small or a big number. If you're at distances that are large compared to 10 to the minus 33 centimeters, it's very weak. But if you start approaching 10 to the minus 33 centimeters, it starts getting strong. Okay? So there's no meaningful sense in which whether it's weak or strong depends on whether you're at long or at short distances. Now, there is another interpretation of what these numbers mean, which is very important, which has to do with quantum mechanics. In quantum mechanics, something you know is that we can't actually predict what happens next when we do one experiment. Okay? If I take two electrons and I fire them at each other, then the electrons can come back out at some angle. Okay? So they fire them in here, they can come out at 30 degrees the first time I do it. I do it a second time, exactly the same conditions, it might come out at 90 degrees. It might come out at 70 degrees. Okay? So we can't predict what happens next. It's the crucial feature of the quantum mechanical universe. Instead, what we can predict are what are called probabilities. And there's a peculiar rule in quantum mechanics that tells you to get the probabilities, you actually have to calculate something else called an amplitude and square that number. Never mind what this means exactly, so probabilities and amplitudes are basically the same thing, but we have to square the amplitude to get the probability. Now, what do these small numbers that we talked about, or what are the numbers that we talked about before mean in this context? It means if I take two electrons and I scatter them together, again, I don't know what happens next, but there's some probability that they might come out at 40 degrees, 50 degrees, okay? There's some probability that nothing will happen at all. They'll just pass through each other. The overall chance that anything happens, they actually scatter, let's say, at more than 40 degrees, that amplitude is set exactly by this small number. It's this charge squared. It's around 1%. Okay? Now, that's a much more specific sense in which these numbers are telling you something about the tininess of these interactions. If you fire electrons at each other, most of the time they don't do anything. Some fraction of the time, around 1% of the time, they'll scatter at some angle. Of course, we can't predict which angle, but we can predict the probabilities it comes out at various angles. But all those probabilities have this whomping 1% all squared sitting in front of them. Okay? So it's a small probability for this to happen. Now, gravity is completely different, and this is a sort of central mystery of gravity. If we do exactly the same thing for gravity, we find that, again, precisely because G Newton has units, that this amplitude, instead of just being a number like 1%, is G Newton times the energy squared. So this number, this probability is like so ridiculously tiny at the normal energies that we talk about. It's a truly minuscule, minuscule, minuscule number. And at energies that are less than 10 to the 19 GeV, gargantuan, enormous energy scale, this is minuscule. But on the other hand, it grows. And as we go to higher and higher energies that in quantum mechanics corresponds to shorter and shorter distances, we find eventually that this amplitude starts becoming around 1, or even if I continue this formula, bigger than 1 when I go to big energies. Now, amplitudes bigger than 1 are nonsense, because we have to take them and square them to get a probability. Probabilities all have to add up to 1. We can't have probabilities that are bigger than 1. So this is just telling us, this very simple argument about units tells us something very strange and bad is happening with quantum mechanics and gravity when the energies start approaching these gargantuan energies of order the Planck energy, or as we start getting to these tiny distances of the Planck length. Okay. Now, this argument about units now tells us something quite amazing pretty quickly. So if we go back to the stick figures that we knew before, the interaction between electrons and photons, I told you that strength of the interaction is around 1/137. Remember I told you that all the other forces have basically the same stick figures? Remarkably, the strength of the interactions are also relatively similar. They're not exactly the same, but for example, the strength of this charge for the strong interaction is like 1/10. Okay, it's stronger than that one, but it's still a relatively small number. For the weak interactions, it's like 1/50. Okay, so we have all these numbers, but pure numbers, around 1%, 1/10, and so on. Okay? All right, but why then couldn't we imagine that we have these much, much more complicated interactions? The reason is the following. Let's say we had an interaction that had one more guy coming out, or two more guys, or three more guys. This is a quantum mechanical process that's producing them, and so we need to have some quantum mechanical fluctuation out of the vacuum to produce these particles. But we've seen already, just from the weakness of the force between particles, remember I told you, as the inverse square law, the fact that the force gets weaker as we go to longer and longer distances, is telling you that it's harder and harder to get a quantum fluctuation at larger and larger distances. Conversely, it's easier and easier to get a quantum fluctuation at shorter and shorter distances. But that means that as you go to long distances, it pays for every extra particle that you emit. You have to have some other factor. It's harder and harder to do it. And that means that all of these guys, only these stick figures, can have coefficients that are numbers, pure numbers like this. All the other ones, just like gravity, have some length in front of them, have some length scale in front of them. And that means no matter what the heck the underlying theory of everything is, we don't even know what it is, okay? But there's something maybe up there near the Planck length where fundamentally we need to have a much deeper understanding of what's going on with quantum mechanics and gravity and so on. Whatever there is up there or beyond there, at large enough distances, even if there are such interactions, we won't notice them. They won't be relevant for describing what we see. They'll be tiny. The only things that will survive, the only things that we will detect and notice and we can use to build our interactions are these basic stick figures. Okay? So this is an immediate consequence of thinking about units correctly. It's an incredibly deep fact about nature. That tells us whatever the heck the ultimate theory is, at long distances it's guaranteed to be described by only these basic 3-point stick figure interactions. All right, so the next thing I have to explain to you is why it is that the menu of spins that we have is so restricted. Why do we only get this tiny, tiny set of things that we can have? Now, I'm going to, since as we've discussed a number of times, the basic fundamental structure of how these particles interact makes sense at very high energies, we're going to do an approximation that makes our life very, very simple, and coming back and thinking about the approximation carefully in a little bit is going to be the entire story of the Higgs. So keep that in mind, but let's first make this simple approximation, that if we're imagining we're banging things into each other at incredibly high energies, clearly we can ignore the masses of the particles. Whatever the masses of the particles are, they cannot possibly matter if we're banging them into each other at energies that are much, much, much bigger than the mc squared energies that the particles have. So we're going to do something sort of bold and immediately think just in terms of massless particles. So we want to see what kind of interactions can we have just for massless particles. Now, there's something very interesting about the spin of massless particles. Okay? We'll come back to this again later, but remember we said that the spin is like the electron is like a top, so it can spin this way, it can spin that way, it can spin that way. Okay? It can spin in 3 different directions. But this is a little different. If these particles are moving at the speed of light, because they're massless, if they're moving at the speed of light, so let me actually back up. How do I know that an electron can spin this way and that way and that way? It's very simple. No matter how an electron is moving, let's say it's whizzing along this way, I can always run and catch up with it. So there I'm catching up with it, right? Let's say it's spinning this way. If I turn my head, it'll look like it's spinning that way. If I turn my head, it'll look like it's spinning that way. So it can spin in all possible ways. Right? But the argument changes the second the particle is massless. Because it's moving at the speed of light, I can never catch up with it. Okay? So I can never stop it and turn my head to see that it's actually spinning in every possible way. And in fact, this is a remarkable fact. The only spins that massless particles can have are spins in their direction of motion or oppositely oriented to their direction of motion. So this is often called helicity instead of spin, just because you kind of think of it as some kind of helical motion around the direction in which the particle is going. Okay? Also, the fact that the particle is massless tells us there's a very simple relation between its energy and the momentum that it carries. If I have a photon that's barreling along in this direction, if it hits me or a block of metal or something, it'll move the block a little bit. The block picks up some momentum. The amount of momentum that it picks up is just the energy that the photon has is the momentum that it has. It's the size of the momentum that it has. A very, very simple relation. Okay. Okay. All right. So So let's now try to understand why it is that we only have this tiny menu of possible spins. And to do that, I want to start off by thinking about what seems like the simplest possible kind of interaction that I can have between two particles. Two particles come in, and they go out and somehow. And there's some amplitude for this process, the words that we talked about before. Now, what can this possibly depend on? It can actually depend on a lot. It can depend on the energy that these particles have, and it can depend on the angle that it comes out at. It can depend on many things. It can be a complicated function of the energy and the angle. And we can't actually just predict it just from pure thought or from for some first principles. But that's fine, because the elementary interactions we're allowed to have aren't these 4-point interactions. They're those basic 3-point interactions. So let's think about what the kind of 3-point interactions that we can have. And now this is an incredibly different story. See, if I have a massless particle moving along, it's very easy to see that by conserving energy and momentum, it can't actually split into two other massless particles that are going out at some funny angles. All it can do is split into two other massless particles that are moving right in the direction that the first one is moving in. So there's no dependence on any angle. There's no angles involved here at all. Okay? All it can do is split into two of them. Now, could it depend on the energy? Well, because of relativity, it can't depend on the energy. If I go to some different frame of reference, I'll still see that this guy is moving at the speed of light, but it'll have a different energy. So by the principle of relativity, it can't be that this depends on the energy. So it seems to depend on nothing at all. It doesn't depend on the energy, doesn't depend on the angle. In fact, all it depends on are the spins of these particles, A, B, and C. And once you give them, you can completely determine what that interaction is. It's amazing. Okay? This is an example of inevitability. Okay? You just declare the principles of relativity and quantum mechanics, and the structure of this triple interaction is completely fixed just up to its overall strength. It's the only thing that we don't know. All right? So now let's return to the problem, but so far we still have spin 17,000 particles floating around. Okay? Now let's return to the general problem. Let's say we want to see what happens in a more normal situation with two particles come in, they bang into each other, two particles go out. There are some very general principles of quantum mechanics and relativity again that tell you very basic things, like when can this amplitude become big? It can become big if you can actually produce a real particle, not one of these virtual particles that we're talking about, but an actual real particle. And when it becomes big, this thing has got to split into sort of making that real particle and having it go out on the other side and doing that. So remember, these elementary interactions we know everything about. We know everything about them because they're totally determined by the spins and nothing else. And so this is now just a completely well-posed mathematical problem. I have to see if I can write down some function of the energies and the angles that when it gets big, it turns out to be representable in this way. So now we have a completely beautifully, that this is a consistency condition. Relativity in quantum mechanics forces it to look like that. Now we can see, is it possible? Is it possible to make it work? This is one of the places that you've got to trust me. So we do have to go to grad school after all, okay? So after a year of grad school, it's just a one-page argument. I mean, I could write out the argument for you on one page. It would mean nothing to you. It's a very simple argument, but you do, after all, need to go to grad school for a little bit to understand this. But it turns out that it has a dramatic answer, that you can't actually do it almost at all, except in these very, very special cases. The spins that you can have are 0, 1/2, 1, 3/2, and 2. Those are the only possibilities. And furthermore, and all you can pick then, the only freedom, this guy's got to be unique. You can have a bunch of these, you can have a bunch of these, you can have any number of these that you want in principle. So that's it. All you get to pick, the only freedom is what is this menu exactly, and what are those interaction strengths. Okay? Now, if you went to Juan's talk, so nothing in this talk has looked like the things Juan was talking about. Okay? If you went to his talk, he had this beautiful financial analog for gauge theories and arbitrage and so on and so forth. And so nothing in the description that I talked about looks like that. The relation between the two of them is that what Juan referred to as the beautiful gauge symmetries are a very convenient language for describing the physics that we are talking about. In fact, what's really convenient about them is the way I phrase the problem: two things come in, two things go out, and you don't much care about talking about exactly how it happened in between. But if you want to describe things in a way where you can give a picture for what happened in between with things banging into each other and so on and so forth, you have to use this beautiful picture that Juan described. Okay, so we've now learned whatever the underlying laws of physics are, at long distances they must be described. First of all, the only interactions we notice are these little stick figure interactions. Secondly, they have to be, the only menu we can have is 0, 1/2, 1, 3/2, and 2. What we appear to have seen in nature, a little puzzlingly, seems to only be a little subset of that. We've only seen 1/2, 1, and 2 for the spins. So what about the Higgs? All right. So now the story of the Higgs actually starts by noticing an amazing difference between massive and massless particles with spin. So let's say I have a massive particle of spin 1. This is just the argument we went through a second ago. I can always stop it. I can move with it so it's stopped, and then I can see that it can spin in 3 different directions. But the massless particle I can't do. It only has 2 ways that it can spin. So we said that we'd like to go to high energies and somehow ignore the mass. Forget about the mass. It's not really relevant. But we can't quite do it because there is this big difference. There's 3 of these versus just 2 of these. Okay? There's one extra way that something can spin when it's massive that's absent when we try to describe it in a massless way. There's one extra guy here when it's a spin 1 particle. Remember, these W particles have spin 1. So the whole story is going to be about this one extra guy. Okay. Let's actually look at what that one extra guy looks like. So let's say I have a W particle sitting here, and suppose that it's spinning up like this, but I boost it so that it's moving along really fast in that direction. Well, according to the rules of relativity, it still looks like it's spinning up like that. Okay, nothing has changed. If it's spinning this way, well, then it looks just exactly the same like that. But let's say that it happens to be spinning in the direction in which it's now going to be boosted. Then, loosely speaking, this is not quite correct, but loosely speaking, if you've heard of things like length contraction or time dilation or things like that in relativity, it's not really that the spin itself gets bigger in this direction, but roughly speaking, the amplitude to find this particle spinning in the direction that it's moving in grows with the energy. In fact, it goes like the energy divided by the mass of the particle, in the limit as the energy is very, very big compared to the mass. So the ones that are not spinning in the direction that it's moving at are unaffected. But the ones that are start getting bigger and bigger as we go to higher energies. Now we're in big trouble. Now we're in very big trouble, because let's take two of these W particles, and then let's collide them with each other. And let's look at what these amplitudes look like. I told you before that all these are just small numbers, 1%, just tiny numbers, everything is fine. Okay, these amplitudes are like q squared is around 1%. But if they happen to be spinning in the direction that they're moving in, then the strength of the interaction is just 1%, but the amplitude to find them in that state is growing with energy. And so this amplitude actually starts growing with energy again. So this number is small, but it starts growing with energy again. Now we're in trouble, because again, if this amplitude gets bigger than 1, everything is nonsense, probabilities are bigger than 1, everything is breaking down. So that tells us there's some energy at which this just really goes to hell. Okay? And you can be very precise about it. The mass of the W particle is 80 GeV, 80 times the mass of the proton. There's a percent, you put 80 there. You work out when is that around 1, and you find that it's around 1 when you put some more numbers in, when the energy is bigger than 1200 GeV. Okay? So there's a real problem. When the energy is bigger than 1200 GeV, everything is breaking down. We don't understand what's going on. Probabilities are getting bigger than 1 when we just collide these W particles together. There are other problems of this sort. If you collide two W particles and produce top quarks, again, the amplitudes become nonsense, bigger than 1, around when the energies are around 1000 GeV. So we might have had this sort of naive picture from everything that we talked about before, that here we are down here, we've seen W's and Z's and everything else at energies of hundreds of GeV, and then we just sail up to very high energies, and somewhere near the Planck scale, maybe, we don't know what's going on. At this gargantuan energy scale, we don't know what's going on. That's a naive expectation. But the actual situation was that something new had to be happening right above our noses, just within a factor of 10 of where we'd been already, just from this argument. Okay, this we knew. Again, no ifs, ands, or buts. All of this was just nailed and forced on us by everything we understand, just relativity and quantum mechanics and nothing else. Okay? So, what could it be? Well, okay, the most naive thing that you might think that it could be is that, well, okay, something new has got to happen at around 1200 GeV. Okay? It's a little too bad because we're stuck down at hundreds of GeV. It's a decade. These decades take 20 or 30 years for experimentalists to get to. So you might just think, oh, well, you just sit there, you wait for experimentalists to get up there, we'll discover all sorts of new stuff. But some theorists were more impatient than that. And they decided to try to see whether they could see some effect of this fact that everything was breaking down at around 1200 GeV, if they could see it in a more indirect way. So for example, here are this L stands for those spins of the W's that give us trouble. So I told you there's also Z particles. So we can have Z particles and Z particles here interacting virtually with these W's that pop in and out of the vacuum. And this gives some correction to the way this Z particle couples to electrons, let's say. It's a tiny correction, but detailed theoretical calculations around 1989, 1990 were done, and they found that, again, if we assume that there's nothing new till around 1000 GeV, that there are 1% level corrections. 1% level corrections to how the Z couples to ordinary matter. It's a tiny effect, okay? And these were difficult sort of tour de force theoretical calculations that were done by theorists in this period to find these tiny corrections. Now, our experimental colleagues were even more ambitious. They said, great, thank you very much. You gave us a target. We should expect interesting 1% level corrections. So we're going to go measure these things to 0.1% accuracy. Okay? And they did that. So in exactly the same period, 1989 to 1991, people measured exactly these couplings between Z's and electrons, and also a related effect just on the masses of the W and the Z particles, and they measured them to 0.1% accuracy. And what they found was amazing. So here are some, these are the size of these deviations in units of 0.1%. And what they found is that, here's what they found. There's some sort of experimental error band. But what you got from assuming that we just went all the way up to 1,000 GeV and something new happened up there was far outside the experimental error bars. Okay? So you would predict that something that was a 1% big, which sounds tiny, but the experimentalists are better than that. They measure to 0.1%, it ain't there. Okay? So this is quite remarkable, because it told us that actually something new had to happen even earlier. It had to happen even earlier than 1,000 GeV. It had to happen beneath around 200 GeV or so. So we need something new, and right around the corner, something new. And what is the job of this something new? It has to solve this problem. We have these amplitudes, we scatter these W's, the probabilities are getting bigger and bigger, dangerously bigger and bigger. Something has to change this calculus. Something has to change this argument. Something new has got to be there. Instead of interacting like this, there's got to be something new. Let's call it X, such that when you add this way of doing it and this way of doing it, the amplitudes don't grow anymore. Similarly, I told you we had a problem with W's interacting with top quarks. Well, there had to be something there again. So see, whatever the heck this thing is, it has to have some interactions with the W, it has to have some interactions with the top quark. All right, so now we know all these constraints about what possible theories can look like. So let's ask a very basic question. What could the spin of this particle be? Well, it turns out that the 1/2, 3/2, and so on, those are just ruled out for a very simple reason. So it could be 0, 1, 2, 3, 4, and so on. Well, it can't be 3, 4, all these higher ones. We threw all of them out already. It can't be 2 because we said there's a unique spin 2 particle. It's the graviton. There can't be anything else. It could be 1. It could have been 1. But that's a little funny because we'd have some massive spin 1 particle, but this whole problem that we got was from a massive spin 1 particle. So we don't want to have a sort of Russian doll of like introducing a spin 1 particle and then introducing another guy for that and keep going on forever. It's not ruled out, but it's very ugly and strange. So we're left with a unique possibility. It has to have spin 0. Okay? When this guy spins 0, it's called the Higgs. This particle is called the Higgs. So I won't, it's an interesting point. If we go to very high energies, this, what we call the Higgs particle, and these longitudinal components of the W and the Z particles are actually united together. They're united together into one object, and this one object interacts with W's and top quarks and everything else by all the usual allowed interactions that we talked about before. Okay? Now this was a brave proposal. Because, as you've seen, no one had ever seen a spin 0 particle in nature before. Okay? So it's an interesting situation. Just from the consistency of the laws, we could have it, but no one had seen it before. And yet we seem to be led into needing it in order to deal with this problem. So you make the proposal. And of course, it was discovered on July 4th. But I want to just say a little word. I won't go through these pretty pictures of how the LHC works. Well, this is not a pretty picture anyway. But so anyway, we collide particles at very high energies, and we measure them in gigantic detectors with European Union issued people smiling in front of them always in pictures. But I want to talk about how it was that the Higgs was actually produced at the LHC, because this shows how completely constrained this entire story was. Again, no choices. There was absolutely no other way that things could have gone. How do we produce Higgs? At the LHC, we bang protons into each other. And I didn't mention it, but the Higgs has these big couplings to W particles and to top quarks. It has much smaller W and Z particles into top quarks. It has much smaller couplings to everything else. They're also nailed, but they're much smaller. And those things don't seem to be inside the proton. The proton has up and down quarks and gluons in it. Well, you produce it through a quite indirect way. Two gluons come out of the proton. They excite a top quark and an anti-top quark out of the vacuum. And now that top quark can talk to the Higgs. Now remember, that interaction strength is completely nailed from our arguments, from what the purpose in life of the Higgs was. There's no choice for what that coupling could be. And so the rate for producing the Higgs is completely nailed. We can't do anything about it. So it's some number. We can't change it by a factor of 2 here or there. It is what it is. Okay, now this unfortunately doesn't come out wearing a name tag saying I am the Higgs. The Higgs particle decays in a blink of an eye in around 10 to the minus 22 seconds to ordinary particles. But when it decays when it decays the way it wants to do most of the time to these things called bottom quarks, it's very, very hard to see. At the LHC has maybe made around 500,000 Higgses up to now. That sounds like a lot, but when it decays into these bottom quarks like it does almost all the time, unfortunately, the bottom quarks are made billions of times through much more ordinary processes. So this is a very, very hard way of seeing them. So you have to see it in a much more rare way. The Higgs can, again, through one of these virtual processes producing W's, then decay to 2 photons. This coupling of the Higgs to the W was also nailed. These were the 2 couplings that were completely nailed from our considerations. We could do nothing about it. So the rate that this happens is nailed. The rate with which it's produced is nailed. And so we have to get that answer and nothing else. The only thing we don't know is the exact mass of the Higgs particle. But from these precise measurements we'd done a long time ago, we knew that it had to be somewhere between 80 to around 200 times the mass of the proton, somewhere in that range. That's all we knew. And that's where it was seen, in exactly that range. Okay? So here's the Higgs decaying to 2 photons. The way you can see that it decays, that it's the Higgs doing it and not some more normal process, is if you make the Higgs and it decays to a couple of photons, every time it does that, the sort of energies of the photons have got to add up to be the mass of the Higgs. So more ordinary processes will spit out photons left, right, and center, but the Higgs will keep piling them up in one place again and again and again. And so you should find, if you look at events that have 2 photons, you should find a bump in it. Okay? The size of this bump, how big it is completely predicted by these considerations, and it worked. Okay? So this was, I think, a triumph for experiment, of course, but also a triumph for theory. It tells us that physics works, and that belief in principles paid off. Okay? So we saw that what we were allowed to have on general grounds were 0, 1/2, 1, 3/2, and 2. We hadn't seen 0 and 3/2. We were led to saying this thing has got to be there. We've never seen one before, but by these arguments, by our little detective story, it's got to be there, and by God it is. It's allowed to be there, it can be there, it is there. Okay? And that's what's exciting about the Higgs. It's the first really new particle that we've seen. It's the first particle we've seen that has spin 0. Okay? The other ones have had 1, 1/2, and 2. All right, so let me just end the Higgs story by now relating a couple of the metaphors that you've probably seen a number of times. One metaphor, so nowhere here have we used a lot of the usual language. The Higgs gives mass to particles. The Higgs is like some fluid or molasses that particles move in and they get their mass from interacting with it. This molasses metaphor is just truly terrible. I've used it myself, but it's terrible, it's misleading, worse than misleading, it's wrong. Okay, so this is just really false. There's another picture that you often see, which is perfectly fine, it's correct. You might see pictures of things that look like these little Mexican hats, and we say the Higgs could sit up there, but it's not stable, and it rolls down there. If you haven't seen them, don't worry about it. But this is a picture of using the language of what's called broken symmetry, and this is perfectly good, it's useful, it's a good language for describing the physics. It's one language for describing it. It's not, there are other languages for describing it, and what we've talked about here has been another language. We didn't need to use any of that. And the advantage of talking about it in the way that I've talked about it here is that you see why it's necessary. Okay? It's not just something that that we like, but it's really necessary. All right, so I'm done. I'm not going to have time to talk about the Higgs mysteries because Robert is walking up. But let me just say one thing. So something which is there are real puzzles associated with the Higgs. The fact that 2 is not equal to 3 is very important, okay? And the fact that 1 equals 1 is even more important. But something that you've probably heard many times in talks like this is this idea of supersymmetry, that there's difficulties with the Higgs, and supersymmetry is a wonderful way of dealing with these difficulties with the Higgs. The language that I'm using in this talk really drives the point home, I think, even more in an even more direct way. You see, we had this menu, 1/2, 1, and 2. So we had the allowed menu, 0, 1/2, 1, 3/2, and 2. And we saw that nature seemed to have only used a small portion of them until it came to the Higgs, and it used the 0. Okay? But the part of the talk that I can't talk about because Robert will kill me is says that there's lots of mysteries associated with that. And then if you just look and say, geez, why don't we see that 3/2? Okay? Well, it turns out that if you go through this 1 year of grad school exercise, you discover that that 3/2 is associated with this idea of supersymmetry. Okay? You have to have this idea of supersymmetry associated with that 3/2. This doubles the world, it does all sorts of wonderful things, but amongst other things, it completely solves this problem. It solves this particular mystery associated with the Higgs. And there are ways that we can, and we are looking for supersymmetry at the, LHC. We haven't seen it yet, but it's something that we are looking for. But all I want to say for the purposes of this talk is that the reason why there's so much excitement about supersymmetry is it doesn't mean that it has to be right, but it's the last remaining thing. It's the last thing that nature could do in principle that we haven't seen it do. And we saw something fairly dramatic with the Higgs already. We saw the 0 option used, so it's not crazy that it's going to come along with the whole thing. And we'll finally see the whole panoply actually used in the way nature works. That's another example of the sort of thing we love in theoretical physics. The ideas we don't know necessarily if they're realized in nature, but there's something rigid and perfect about them and inevitable about them just as theoretical possibilities. And thinking about what's inevitable and rigid leads us to, first of all, it's a very strong constraint on theoretical speculations. We can't mess with the rules that we have already. And it leads us to a tiny set of possibilities for what might actually be there. Okay? And maybe one of, or some of them are hopefully realized in nature. Okay, so let me just end by saying that, no, this is really ending. That space-time and quantum mechanics really framed the central dramas of the 20th century and really have taken us shockingly far. We've seen that the story of the Higgs is the last example of how shockingly far it took us. But in a sense, this whole story of the Higgs is the last, one of the last embers of the set of ideas that we dealt with and understood in the 20th century. The real drama, and again, these ideas, inevitability, rigidity, and fragility, and beauty are we've seen, I hope, over and over again in this talk. But the real drama of the 21st century are really new questions. We saw that it's really relativity and quantum mechanics, this picture of space-time that Einstein gave us in quantum mechanics that's been so shockingly rigid and powerful. So the next set of questions are, where do these things come from? See, that's one thing I didn't question. I just took space-time and quantum mechanics, and all the rest of it followed. So this is really the next set of questions. What's the deeper origin of space-time and quantum mechanics? And this is what you should ask your friendly neighborhood string theorist to tell you about. Okay? And in fact, I really hope that if you should stay tuned for IA's public lectures sometime between 2020 and 2030, and we might have a little bit to say about these questions. Thank you very much.
Well, another description I've heard of NEMA is as the fifth force of nature, which works well. And thank you for having this trailer of the second public talk that you will go give fast. I want to, we are a bit constrained in time, but I want just to give an opportunity for, say, one question. Is anybody volunteering to ask a pressing question? Yes, over there. I think there will be a microphone.
So it's not a question, it's a comment. I'm probably one of the few people in the room that's not a physicist, but what struck me with the words, your choice of words, inevitable, rigid, fragile, and beauty, is they all conjured up an image of truth to me.
Yeah.
And so I
Well,
wanted to share that with you.
You know, in other talks in this venue, I've used this opportunity to say how incredibly apt the seal of the Institute is, which has, you know, truth and beauty sitting right next to each other. Actually, interestingly, you know, there are two relatively scantily clad ladies. It's truth which is naked, and beauty which is veiled in the seal. That may tell us something about the kind of work we're doing here. But indeed, yeah. Everyone who works in this subject knows that, you know, we're all very, very, very. We have very poor intuition for the way things work. Some of us are much less talented than others of us, but it doesn't matter so long as you're somewhere in the basin of attraction of the truth. The truth is an incredibly powerful thing that, so long as you don't fight it, sucks you in towards the way things work, and we really have it on our side. Yeah, truth with a capital T, absolutely.
Well, thank you. I think perfect closing segment of this night. Thank you very much again.
Thank you.